This is the second part of probability, and we start off with independent versus dependent probability. What exactly does that mean? Well, two events that can occur are independent if they don't affect each other. For example, the flipping of a coin, right? If I flip head in my first try, does that affect my chances of flipping head in my second try? No, it doesn't. Each time I flip the coin, I have a 50-50 chance of flipping a head or a tail. But on the other hand, suppose I'm taking a penalty in a football game, right? Me missing the shot may reduce the chances of me scoring my next shot because my confidence is low. Therefore, the events of taking a pen are dependent on one another, while the flipping of a coin is independent of one another. Let's take an example here. So a bag contains 3 red counters and 7 green counters, and a counter is randomly picked and then replaced, meaning you pick it, then you put it back. Find the probability of getting 2 greens. The probability of getting 1 green counter is 7 over 10 because there are 7 green counters over a total of 10 counters. Then you are replacing it again, and you want those 7 green counters again, so you'll multiply by 7 over 10 again, and this will just give you 0.49. That's going to be the probability of you picking 2 greens in a row. Then what about picking one of each color? Now remember, you can pick a red first and then you can pick a green, or you can pick a green first and then you can pick a red. When you want to pick a red first then a green, remember you're replacing them after you pick them out. The probability will be as follows: 3 over 10, because 3 red over 10 counters in total, times 7 over 10, 7 green over 10 counters in total. Then you have another option as well, where you start off with the green, so 7 over 10 times 3 over 10. What this does, the first part gives you 0.21, second part gives you 0.21 again. Remember, you can do this or this. Remember how we discussed or in terms of probabilities will be you adding those probabilities up. Therefore, total probability of you getting one of each color, which can be in either of these formats, will be 0.42 in total. Now it brings us to a condition. When 2 or more events are independent to one another, then you have this condition that is met. The probability of A and B, meaning both of them happening, event A happening and event B happening, is equal to the probability of A intersection B. This we discussed in the previous lesson. And that will be equal to the probability of A on its own multiplied by the probability of B on its own. As you can see, these two examples are exactly that. These events are independent to one another. The picking of a green and then picking of a green again, they are independent because of that replacement. Same thing if you have more than one event, where you'll just keep on multiplying them. Now, what if the counters were not replaced? Meaning, once you pick them out, then they stay out. What happens for you getting 2 greens is the first time you have 7 possible successes out of 10 possible counters. Then you have reduced the green by 1. So now you have 6 greens remaining because that 1 is not replaced that you picked out initially, over a total of 9 counters because again you have removed 1. This will then give you 42 over 90 as your probability. On the other hand, when you're picking one of each color, same thing happens. You can pick again red then green, or you can pick green then red, one of the two. When you're picking red then green, the first time you pick, you have 3 reds out of a possible 10 counters. Then you keep that red out. And so when you're picking green, you have a possible of 7 greens out of 9 possible counters, which gives you 21 over 90 as your probability of picking red then green. What about the probability of picking green then red? Again, similarly, you have 7 greens out of 10. multiplied by, you have removed that green now. So you have, again, 3 reds remaining out of 9 total counters, which again gives you 21 over 90. Which then if you add together, because remember, you have an or, you have red then green or green then red, you'll get a total of 42 over 90. That will be your probability of you getting one of each color. As for application of the multiplication law that we saw in the previous slide, it can be used to determine if events are independent or not. What did we say? We said P of R and G, two events happening both together. So an AND condition, R and G happening, will be equal to P of R, probability of R, event R happening, multiplied by probability of event G happening. Remember, the probability of event R happening is picking up R from your bag, which is just 3 over 10. Probability of G happening individually is just picking a green from your bag, which is 7 over 10. The probability of both happening in this example, because remember we did not replace, was, as we said, 21 over 90, as what they're saying here. While this on the right side is just 21 over 100. Are these equal to each other? They are not. And because they're not equal to each other, we say that they are not independent. If they would be equal to each other, then yes, they would be independent. Next, let's look at combined events. Two ordinary fair dice are rolled and their score is summed. Draw a possible outcomes diagram. So, you roll them twice and the score is summed up together. So, on the first throw, we can get a 1, we can get a 2, we can get a 3, we can get a 4, up to 6. On the second one, we can get, again, the same thing. 1, 2, 3, 4, 5, and 6. If in the first try we roll a 1 and the second try we roll a 1 again, the sum will be 2. If in the first throw we roll a 2 and in the second throw we roll a 1, our score will be 3. And we can do that for all of the outcomes. There will be a total of 36 outcomes. And I'll fill the table for you right now. That's going to be the possible outcomes diagram. These are all your possible outcomes that are there, the ones in red. Then we have to use this diagram to work out the probability that the sum is greater than 8. Now remember, the total possible outcomes, they are 36. If you count how many outcomes there are here. 6 in the rows and 6 in the column, 6 and 6 is 36 total outcomes. We want to find when the sum is greater than 8. So we start from here, where you have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So 10 possible outcomes when the sum is greater than 8 or 9 and above 10. That's going to be your probability that your sum is greater than 8. Then in the second one, we are told to find the probability that the sum is a prime number. Now what are the prime numbers? We have 2, we have 3, we have 5, we have 7, and we have 11. In total, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So 15 out of the 36 outcomes have a sum that is prime number. Finally, we are told to find the probability that the sum is a factor of 24. Now, what are the factors of 24? We have 1, 2, 3, 4, 6, 8, 12, and 24. So just have to find where do we get these numbers. We have 2, we have 3, we have 4, we have 6, we have 8, and we have 12. In total, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So we have 17 possible outcomes where the sum is a factor of 24. 17 out of 36. So that's going to be the probability of that. Next up, we are told that 3 ordinary fair dice are rolled and the score is summed. We have to find the probability that the sum is less than 5. Now, there are only 2 possible options here that we can get for our sum to be less than 5 if we roll 3 dice. That is if we get a score of 3 or if we get a score of 4. From your 3 dice, to get a score of 3, you have to get 1 on each roll for each dice. To get a score of 4, you can get 1 on 2 of them and 2 on the last one. Or remember, you can get that 2 in the middle one as well. You can get that 2 on the first one as well. And so these 4 are your options that are there for you to get a sum that is less than 5. Now, how many total possibilities are there? How many total outcomes are there? Remember in the previous one, when we had 2 dice, we had a total of 36 outcomes. Why? 6 possible options in the first dice and 6 possible options in the second dice. So 6 times 6 gave us 36. Now we have 3 dice. And so we have 6 possible options in the first one, 6 possible options in the second one, and 6 possible options in the third one, which gives us a total of 216 total possible outcomes for the score. From that, only 4 of them give us a sum that is less than 5. So our probability is the success outcomes, which is 4 possible outcomes, out of the possible 216 outcomes. That's going to be our probability. Next, we are told that Abba passes through 3 independent sets of traffic lights when she drives to work. The probability that she has to stop at any particular set of lights is 0.2. Find the probability that Abba has to first stop at the second set of lights, or she has to stop at exactly 1 set of lights, or she has to stop at any set of lights. So what we can do here is display this using a tree diagram, because it's a dichotomy, meaning there are only 2 possible options, that she stops or she doesn't stop. So we're going to write this: the first set of lights, the second set of lights, and the third set of lights. First set of lights, she has an option to stop or not to stop. Then second set of lights, again she has an option to stop or not to stop. Then again third set of lights, she has an option to stop and not to stop. Let's do this for all the possible scenarios. This is the tree diagram that you get after you put up all possible scenarios. And now we have to add the probabilities for each of these decisions. Remember, probability that she has to stop at any set of lights is 0.2. So let's just add that. And obviously, not to stop will be the remaining, because it's the complement of stopping, so 0.8. Then it says that, what's the probability that she has to first stop at the second set of lights? So in the first set of lights, she doesn't stop, but she stops in the second set of lights. That means what we want here is that the first decision is not stopping, and then the second decision is stopping. And so we want these 2 to happen. Whatever else happens after that doesn't matter, but we want these 2 events to occur. And so we will take the probability of that, which is going to be 0.8, multiplied by 0.2, because we want both of these to happen, which gives us a probability of 0.16. And so we have a probability of 0.16 that she first stops at the second set of lights. Then the second one says that she has to stop at exactly 1 set of lights. Now, I'll do something to make this easier for us. I'll write down in terms of letters what exactly the decisions are. So here is SSS, here is SSN, here is SNS, here is SNN. So I've written down all the possible options from all of these decisions. So there are 8 possible outcomes that occur. Stops on all 3 lights, stops on the first 2, and then doesn't stop on the third one, and so on. Here what it asks is that she has to stop at exactly 1 set of lights. Which one are those scenarios? It's this one right here, where she stops only on the first one. This one right here, where she stops only in the second one. And this one right here, where she stops only in the third one. Then for each of these, we're going to find their probabilities. So S and N has 0.2 times 0.8 times 0.8. Same thing with here. We have 0.8 times 0.2 times 0.8. And same thing here, we have 0.8 times 0.8 times 0.2. The reason they are the same is because they are independent events. And so what we will do is just add all of these together, because these three are the possible options that you have. It can be either one of them. And so what we get is 0.128 multiplied by 3, and we get 0.384. That's going to be your probability that she has to stop at exactly one set of lights. We are then told to find the probability that she has to stop at any set of lights, meaning she has to stop at least once. She stops at least once in all of these possibilities apart from the last one. Therefore, we want the complement of the last one. Remember, if we have an outcome plus the complement of the outcome, we get a total probability of 1, because it's just something happening or something not happening. And so since all of this all ties into the complement of that last option, what we can do is just use this formula where you're doing 1 minus the probability of not stopping at either of the traffic lights, which we get by doing 0.8 times 0.8 times 0.8 right here. From that we get 0.512. So what we're doing here is just 1 minus 0.512, and we get out of this 0.488. That's going to be the probability that they stop at least one of the lights, or the probability that they don't always not stop. Basically the complement of always not stopping. We're now told that the events J, K, and L are independent, given that the probability of J alone is 0.5, the probability of K alone is 0.6, and the probability of J and L is 0.24. We have to find the probability of these following. So to find the probability of J and K both happening, remember, because they are independent, P, J, and K is equal to just P of J, probability of J, multiplied by the probability of K, which is just 0.5 times 0.6, which just gives us 0.3. That's quite simple. Then we're told to find the probability of L on its own. The only thing we're given is this here that involves L. But we know that the events are independent. So we know that P of J intersection L is equal to the probability of J multiplied by the probability of L. The probability of J and L is 0.24. Probability of J alone is 0.5. And from that we can find what the probability of L is. We can divide by 0.5 on both sides, and we get that the probability of L is just 0.48. Finally, we're told to find the probability of K intersection L. Again, because they're independent, probability of K intersection L is equal to the probability of K alone multiplied by the probability of L alone. And that is going to equal to 0.6 multiplied by 0.48, as we found in the previous part, which gives us 0.288 in total. So the probability of K intersection L is just 0.288. Finally, we are told that in a group of 60 students, 27 are male, 20 study history, and the Venn diagram shows the number of students in these and other categories. One student is selected at random from this group right here. Now we have to show that the events a male is selected and a student who studies history is selected are independent. So what we have to do basically is just show this is equal to probability of M multiplied by the probability of H, because that's the condition for independence. If they are equal to one another, then we know that the events are independent of one another. So what's the probability of getting male alone out of this entire group? Remember, the entire group has 60 students and males are 18 plus 9, which is 27. So 27 over 60. Then what about the probability of a history student? History student is 11 plus 9. There are a total of 20 history students out of 60. So 20 divided by 60. On the other hand, what's the probability of you getting male and a history student? That is just 9, because there are 9 total students that are male and do history. So we have 9 over 60 here. What we do get on the left after simplifying is 3 over 20. And what we do get on the right is 9 over 20 multiplied by 1 over 3, which actually is just 3 over 20. And because these two are equal to one another, then we get that these two events that a male is selected, so the event M, and the other event that a student who studies history is selected, so the event H, are independent, because that condition was fulfilled, this condition right here.